I want to take a moment to talk about a few different types of discrete random variables. Now, by no means are these all the different types of discrete random variables you'll encounter, but it's a good starter set. And anytime you encounter a discrete random variable, chances are one of these guys is the culprit. So let's start with the binomial distribution. And actually, one last thing. Before we start talking about any of these, I don't want to get into the nitty-gritty details like about numbers or means or variances or probabilities. I want to try and keep things as simple as possible and merely talk about the structure behind these discrete random variables. So starting with the binomial, I want to point out that there's 20 copies printed. What do I mean by that? I want you to envision that you're working at a copy shop. So you're working at a print shop like, I don't know, FedEx or Kinko's or whatever. And when you print a copy, there's a chance that it's bad, like their ink has run out or everything got printed backwards. That's what we consider a defect. And let's say that that happens 10% of the time. First thing, one of the hallmarks of the binomial distribution is that this probability is consistent. This does not change from term to term. That as I go from one trial to the next, this probability won't change. What do I mean by trial? These are the trials that I'm going to print 20 copies and I'm going to inspect each one for a defect. So here, the other hallmark of the binomial distribution is the finite number of trials. This is going to contrast in a minute with the geometric distribution, but I just want to say that when you're told that there's a finite number of trials being inspected, or we're flipping a coin a finite number of times, or someone's taking a shot at the basketball hoop 5 times only, that's telling you it's a binomial distribution because we're only trying that a finite number of times. A few other things. The binomial distribution is independent, or the trials are independent, so we'll say independent trials. That means the outcome of one trial doesn't affect the next. And we also want to say that there's only 2 outcomes. That makes sense because it's called the binomial distribution. So there's only 2 outcomes. We could talk about a distribution where more than 2 outcomes are possible, and that's called the multinomial distribution, but that's a different video entirely. Let's hop over to the geometric distribution. This distribution, I call this the shoot till you miss distribution, or shoot till you make one, depending on your perspective. So shoot until you miss. Notice there's no fixed number of shots as there were for the binomial distribution. You could conceivably shoot 1,000,000 times and never make a single shot. So you could keep shooting, well, forever. This distribution is called, I call it the shoot till you miss distribution, because we're only concerned with finding out what happens or how likely it is that we keep shooting until finally we get a defect or finally we miss the shot. In this case, we're printing copies. We don't know how many copies we're going to print, but we're going to keep printing copies until the 7th one is bad. And once the 7th one is bad, we stop the simulation and we ask ourselves, how likely was it that that was going to happen? All right, let's hop over to hypergeometric. This looks very similar to binomial distribution insofar as there are 20 copies printed, but this time, as opposed to there being a fixed probability that one of the copies was bad, we know ahead of time that 2 copies are bad. There are 2 defects in this batch of 20 copies. By the way, I am going to use that term for a reason. I'm going to call this the batch. So the batch is the number of copies printed out, and from that batch we're going to take a sample of 10 copies. So I'm going to put batch like this as a rectangle, call this the batch. Use a different marker so it doesn't squeak so much. So this is the batch. And then we've got a sample of 20 copies. So from that batch, we're going to take a sample. Then we're going to thumb through that sample of 10 and see how many are defects. Now remember, there were 2 defects in this batch, but we don't know how many are going to end up in the sample. It could be 0, it could be 1, or we could get both defects in the sample. So this is the hypergeometric distribution. We have a batch from which we take a sample, and some of those items in that batch are defects, or we don't necessarily have to use the phraseology of bad or good or defect or non-defect. But we also talk about this distribution when we're talking about forming committees. One of the most common problems is we might have a committee that's to be formed with 7 members, but we want to draw from a pool of Republicans and a pool of Democrats, or we want to draw from a pool of men and a pool of women. And we want to see that how many different committees can we make from a batch of men and women. That would be the hypergeometric distribution. All right, let's jump over to the Poisson distribution. I know it looks like poison for one, but the Poisson distribution is probably the least like the rest. The Poisson distribution models the number of times an event occurs over a fixed interval of time or a fixed sample size or sample space. One of the best examples is anytime you see how many customers come in this case we're still in the idea of a print shop. Anytime we talk about the number of times a customer comes in over a certain window of time, that's screaming at you this is Poisson distribution. So I'm saying that we're counting the number of times that customers come in per 15-minute window. Of course, we can lengthen that window to an hour or 2 hours or a day, or we can go to as narrow a window as a minute or a second or a millisecond. So counting the number of customers that come in, and this can extend to the number of telephone calls we receive over a 10-minute window or a 15-minute window. It could also extend to, those are the most common examples about phone calls and people coming in during into a shop. But we could also talk about cars that pass by on the road. How often a car passes on the road? If we see like how many cars are going to pass by this intersection in the next hour, that would be modeled with a Poisson distribution with the right assumptions. I want to spend one last second talking about. I said something about it also happening over a fixed space, not just a fixed time interval. So a fixed space might mean, let's say we're looking at a giant sheet of paper, and we want to find where there are defects on the sheet of paper. So let's say defects occur where these little dots are. And so this is the giant sheet of paper, okay? But let's say we only look at small squares at a time. So I might look at this small section, or I might look at this small section, or I might look at this small section. And when I look at small sections of this giant sheet of paper, I'm curious to know how many defects am I likely to observe in a little small subset of that giant sheet of paper. So this is what I mean by finding defects over the course of a space rather than over a time interval. With that said, I think that gives you a nice brief overview of the different types of discrete random variables, or at least the 4 that I wanted to talk about today. And hopefully it gives you an idea what the underlying structure is behind them. So whenever you see a problem that asks you about a different type or asks you about a distribution, you can kind of hone in on what type it is based on these different facts. Hopefully you enjoy the video, and I'll see you guys next time.